Hi all, let's take a look at the Achieve 4.3 homework assignment. You'll notice the first several problems ask you to use the mean value theorem. So if we recall back to section 4.2, if you remember Rolle's theorem just said that if you have a function on an interval a, b, and you know f of a is equal to f of b, then there exists some point c in between a and b where the derivative at that value of c is 0. Okay, well, Rolle's theorem is merely a subset of the mean value theorem. What the mean value theorem is saying, well, okay, what if you have that interval a, b, but f of a does not equal f of b? Well, what it says is that whatever the slope from f of a to f of b is, if you drew a line and found the slope between those 2 points, then there must exist some point c in between a and b where f prime of c is equal to the average rate of change, or the slope, from a to b. So what these first few problems are asking us to do, and one of the weaknesses of Achieve is it can't ask you to go in and do a full-fledged mean value theorem proof, unfortunately. If you'd like to see those, you could look at my traditional book homework assignment for the first few problems in this section, and you can see more what a proof would look like. But what we're doing here is we're just finding that value of x equals c, where the derivative is equal to the average rate of change at that specific value of x on the interval a, b. All right, for example, question 1. It gives us the function x to the negative ninth, or 1 over x to the ninth, and it says on the interval 1 to 2. So first thing I need to do if I'm going to try to show the mean value theorem is I need to figure out how much does this function change and what is the average rate of change, what is the slope from 1 to 2. So I plug in a 1, obviously 1 to any power is 1. I plug in a 2, and I would get 2 to the negative ninth, which is the same thing as 1 over 2 to the ninth. That's 1 over 512. So the slope between 1 and 2, I'll just call it the average rate of change between 1 and 2, is going to be f of 2 minus f of 1, or 1 over 512 minus 1, divided by 2 minus 1. When I did that, went to my calculator, reduced it down, the slope there, or the average rate of change, is negative 511 over 512. So what the mean value theorem guarantees us is that since this function is continuous on this interval between 1 and 2, there must exist some x value equal to c between 1 and 2 where the derivative is equal to that slope between 1 and 2. Okay, so I take my derivative. Derivative of this function is negative 9x to the negative 10th. I rewrote that as negative 9 over x to the 10th. And then I can say, well, I need to set that derivative equal to the average rate of change. Pretty easy to do. In this case, what I did is I multiplied negative 9 times 512 and negative 511 times x to the 10th. I knew that each side would be negative, so I just ignored the negatives. You could divide by a negative and they would cancel out. So 9 times 512 is 4608. That's going to equal 511x to the 10th. Then I can say, well, in order to solve for x, you would divide by 511 on each side, and then x would be the 10th root of that. Now, technically, since it's the even root, you would say it's the positive or negative even root. I knew I was only interested in the positive root since the region of interest was between 1 and 2. And when I took the 10th root of 4608 over 511, I got my 246. And you can see that that's the answer that Achieve wanted. It wanted you to answer to 3 decimal places. You put that answer in and Achieve will like it. For the next problem here, it gave me find all points C. Remember, C is just the values of X within the interval that satisfy the criteria of the mean value theorem. For the function in this case, y is equal to cosine x minus the sine of x from 0 to 2 pi. Okay, so I evaluated my function at 0. Cosine of 0 is 1. Sine of 0 is 0. So y of 0 is 1. And then y evaluated at 2 pi. It's going to be the same thing. Cosine of 2 pi is 1. Sine of 2 pi is 0. So again, I get 1 minus 0. The y value at each of the endpoints is 1. This is actually going to be a Rolle's theorem problem because f of a is equal to f of b. But remember, like I said to begin with in this video, Rolle's theorem is just a subset of the mean value theorem. So we're still doing the mean value theorem. It's just, in this case, it's really Rolle's theorem. So I need to find the average rate of change. And as I can see, they don't change. The y values didn't change, so your slope is 0. So now I just need to take the derivative of this function. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. And then I can say, well, okay, this is going to be a true statement whenever I can say negative cosine is equal to positive sine. And I was just thinking about my unit circle. The values at which the sine and cosine have the exact same values except for the signs are at 3 pi over 4 and 7 pi over 4. They're both the square root of 2 over 2, but they alternate signs. So I can say, well, these are my two angles where that's going to be valid. Now I can go in and say, well, all right, those are the two critical points such that the derivative is 0. Both of these points are going to be values between 0 and 2 pi. So you can see I had to enter both 3 pi over 4 and 7 pi over 4 in my answer, and Achieve liked it. For number 3 here, we have y is equal to x cubed, so pretty simplistic function here, on the interval -2 to 3. So I said, okay, I need to find out the beginning and the ending point. Y evaluated at -2 is -2 cubed. I get -8. Y evaluated at 3 would be 3 cubed for 27. So then the average rate of change is just going to be y2 minus y1, 27 minus a -8, over x2 minus x1, 3 minus a -2. And then you can say, well, all right, your numerator is going to give you 35, denominator difference is 5. That's going to divide out to give you a 7. I know that the slope is 7. Now, what the mean value theorem tells me is that it absolutely guarantees there exists some x equals c for some number between -2 and 3 such that the derivative is also equal to 7. It's guaranteed. So I can say, okay, let's find it. I take the derivative, very easy to take in this problem, 3x squared. We set that equal to 7. We know that this has to be a valid answer for some number between -2 and 3. Well, in order to solve for x, I would divide by 3 on both sides. And then you can say, well, now x squared is equal to 7/3. So that means x could equal both the positive and negative root of 7/3. And if you check the root of 7 over 3, that is even the negative one, it's well within our region, -2 to 3. So both the negative and the positive root need to be put in as solutions. And you'll notice Achieve doesn't have the capability to put that plus minus, so you'll have to enter the two answers in individually. For number 4, still the mean value theorem. This one, it's wanting a decimal answer to 3 decimal places. So this time it's giving me an exponential function. Y is equal to 7e to the -3x minus 7 on the interval 0 to 2. Okay, so I need to evaluate my function at its beginning point and at its end point. F of 0, I know any exponential function raised to the 0 power is 1. So I would just get 7 times 1 minus 7. That's why f of 0 is 0. Now f of 2, if I plug a 2 into this, I would get 7e to the -6th minus 7. I would prefer not to get a decimal for that for now. Now when I go into my average rate of change, the average rate of change from 0 to 2 is going to be f of 2, 7e to the x minus 7, minus f of 0, which is just 0, divided by 2 minus 0. So I knew my answer was this for now, and that's the exact slope. for the average rate of change, 7e to the negative 6 minus 7 over 2. Okay, now my goal is to take the derivative and show that x is equal to this slope for some x value between 0 and 2. That's what the mean value theorem stipulates. So when I take the derivative, I know that the derivative of the minus 7 constant is 0. So this is the only thing I need to worry about that has a derivative. And I remember that the derivative of every single exponential function in existence is that exponential function times the derivative of its exponent. So it's just 7e to the negative 3x times negative 3. That's where the negative 21 came from, 7 times negative 3, multiplying the exponential function e to the negative 3x. I set that equal to my average rate of change, and then I try to solve for x. So the first step I did here in trying to solve for x was I divided both sides by negative 21. If I divide by negative 21, the right-hand side was already divided by 2. So now it's divided by 2 times a negative 21. Now it's divided by a negative 42. Now, the way you get rid of the exponential base e is to take the natural log of both sides. So that's why you'll see the natural log of this fraction I had on the right-hand side. And then finally, to get x all by itself, I would divide by negative 3. And when I did that, I had my decimal answer here. Of course, I just entered that in on the calculator and got my 0.598, and Achieve thought that answer was great. Up next here, we have another mean value theorem problem. Here's my work that I did on mine for this one. I'll show this. Says to find a point C satisfying the conclusion of the mean value theorem for 12x squared. So again, easy problem to work with, at least as far as taking the derivative. The only slightly challenging part of this one is get some fairly large numbers in it. We have 12x to the second from 0 to 11. When we evaluate it at 0, of course, we get a 0. When we evaluate it at 11, we would get 12 times 11 squared, which is 12 times 121, gives me 1,452. So then my average rate of change from 0 to 11 is just y2 minus y1, 1452 minus 0 over x2 minus x1, 11 minus 0. Well, 1452 divided by 11 takes me back to 132. But what this tells me is that the slope from 0 to 11, it's a slope of 132 from one point to another. The y value moves up 132 units per x unit increase over this region. So I know that there has to be some x value in between 0 and 11 that has this exact same instantaneous rate of change. I easily take my derivative using the power rule, set that equal to 132, and then we solve for x by dividing by 24 on each side. Well, 132 divided by 24 is 5.5. And you could have left it as a fraction, but since that decimal is an exact decimal, either one's fine. So 5.5, or if you'd have preferred 11 over 2, either one there. Up next, it's another mean value theorem problem. So it's going back to an exponential function. This is going to be similar to number 4. It's a little bit easier than number 4. We have our exponential function 4e to the x. Now it's on the interval 0 to 3. Okay, so I'm supposed to, and I guess the thing that makes this one a little bit different from number 4 is, unlike number 4, it does not want a calculator answer. It wants an exact answer. So I need to be very precise in my calculations. I can say, okay, no problem. Evaluate the function at the beginning point, y of 0. Any exponential function to the 0 power is 1. 4 times 1 gives me a 4. Then I can say, now evaluate it at 3. It's just going to be 4x to the third. And it is, you have to leave it exact. Don't give me a decimal for 4e to the third. Now, when we do our average rate of change, we would just say, well, it's y2 minus y1, 4e to the third minus 4, divided by 3 minus 0. That's just going to give me, I just didn't even hardly simplify it. I just said 4e cubed minus 4 over 3. I could have factored a 4 in the numerator, I chose not to. So now when I go into my problem and I can say, well, what's the derivative of this exponential function? Derivative of any exponential function is that exponential function, technically times the derivative of the exponent, but that'd be times 1. So this function does not change when you take its derivative. So now I set that derivative equal to my average rate of change and I solve for x. First thing I do is I divide by 4 on each side. When I divide by 4 on the right, I just know that these two terms of 4 are going to become a 1 in the numerator. So I will get e to the x is equal to e cubed minus 1 all over 3. And then I could solve for x by taking the natural log of both sides. So x is going to equal the natural log of this fraction. And put that in on achieved, and you would have the correct answer. Again, on that one, they did not want a decimal. Number 7 is still continuing this mean value theorem logic train. I think it's the last one. Yeah, the next one goes into the first derivative test. So for number 7 here, it's giving me a radical function. I go ahead and write that as 8x to the 1/2 power. And we're supposed to evaluate that from 0 to 13. Clearly, 8 times the square root of 0 is 0. And then for the 13, it's just going to be 8 on the root of 13. It's better if you leave your answers exact. So then my average rate of change formula is going to be 8 on the root of 13 minus 0 divided by 13 minus 0. That just gives me 8 on the root of 13 over 13. Now, I need to show that the derivative is equal to that average rate of change for some value of x between 0 and 13. Shouldn't be hard to do. So the derivative here, 1/2 comes down in front, multiplies the 8, and I get a 4x to the negative 1/2. It's better if you rewrite that back in radical form. I actually think it helps you to solve it. So I said, well, 4x to the negative 1/2 is equal to 4 over the root of x. Now, I need to set that derivative equal to the average rate of change up here. So now when I set that derivative equal to the average rate of change, I can say, well, all right, how do I solve for x? First thing I did is I cross multiplied. I said I'll have 4 times 13 is 52. And then I'll have 8 times the root of 13 times the root of x. That gives me 8 on the root of 13x. Now, what I did at this point in the problem is I said, well, let's get that root of 13x by itself. I divided by 8 on each side. 52 divided by 8 reduces down to 13 over 2. Then I said, okay, I can't solve for x as long as it's inside of a square root. So let's go ahead and square both sides. No problem. 13 over 2 squared gives me 169 over 4. And of course, the square root squared is just what's inside, 13x. Final step in solving for x, you would divide by 13 on each side. 169 divided by 13 is 13. So then it takes me back to x is equal to 13 over 4. And you can see that that is the value of c that satisfies the mean value theorem, obviously in the work here, and achieved like that answer. Now, number 8 starts the problems that will continue through the rest of the section. They all talk about the first derivative test. And the first derivative test is just saying that whenever a derivative is positive, you know the original function is increasing. Whenever a derivative is negative, you know the original function decreases. Whenever the derivative is equal to 0, you have a critical point. Those critical points could be a maximum, a minimum, and it could be an inflection point. It might not be a maximum or a minimum. The way that we decide whether those critical points are maximums and minimums is we look at the sign of the derivative on each side of them. If a derivative is positive before and negative after, I know the critical point is a maximum. If the derivative is negative before and positive after, I know it's a minimum. If the two scenarios, well, what if it's positive before and positive after? It's not a maximum or a minimum. What if it's negative before and negative after? It's not a maximum or a minimum. So the only time you're going to have a maximum or minimum is when the derivative changes sign. So if it changes sign from positive to negative, you have a maximum. If it changes sign from negative to positive, you have a minimum. So pretty straightforward test, and I really try to show my work out very thoroughly in these problems to make it as easy to follow as hopefully possible. So you'll see in this problem, they just asked me to find all of the critical points of 9x cubed minus 27x minus 11. So the critical points are going to be where the derivative is equal to 0. So I take my derivative. It's just simple power rule in this problem. And then once I do that, since I know I need to set it equal to 0, it's best to go ahead and factor. So I factored out a 27. That left me x squared minus 1, which I know is a difference of 2 squares. So I factored it to 27 times x plus 1 times x minus 1. Now I set that equal to 0 to find my critical points, which clearly are going to be at -1 and +1 when you set those factors equal to 0. Now I went ahead and did the chart, this chart that I'm doing in all of these problems 8 through 22, this is the first derivative test. Whenever you break up the domain of the original function with your critical points, and then you're going to test the sign of the derivative in each of these regions. That is the first derivative test. So I said, okay, my original function, it has a domain of -infinity to infinity. I'm going to break up that domain with -1 and 1. So please notice, I go from -infinity to -1, from -1 to 1, and then from 1 to infinity. I choose test points within each of these regions. Nothing special about these numbers other than they do lie in the region they are hoping to test. So I plug a -5 into my first region, a 0 into my second, and a 5 into my third. Now, how do I determine whether the function is increasing, decreasing? Like I said, if the derivative is positive, we know the function's increasing. If the derivative is negative, we know the function's decreasing. So it only makes sense to just go ahead and test those points into the factored version of your derivative. So I put the factored version of my first derivative here. And now I need to do the first derivative sign test. That just means I don't actually care what the first derivative evaluated at -5 is. I don't care what the specific number is. I only care about the sign of that number. So just to emphasize that point, I showed that first factor of 27, well, clearly that's positive, and it's going to remain positive no matter what you plug in. What about the factor x plus 1? If I plug in a factor of if I plug in an x value of -5, x plus 1 is going to be negative. Well, what about x minus 1? Well, when you plug in a -5, that's going to be negative. So I can say, well, then my first derivative evaluated at -5 is guaranteed to be positive. Now, could you literally plug a -5 in there and actually get a number with that? You could. Doesn't matter though. The only thing that we care about is that the first derivative is positive there, which means your function starts off increasing, and it will continue to increase until it hits that critical point at -1. Now we need to find out what happens between -1 and 1. That's what this next region tells me. Plug a 0 into your first derivative factored. You said, well, the first term's always positive. If you plug a 0 into the second factor, it's positive. Plug a 0 into the third factor, it's negative. 2 positives times a negative is a negative. That tells me that my derivative is negative in this region and that the original function is decreasing in this region. And then finally, if you plug in a 5, every single one of your 3 factors would be positive, which means your first derivative is positive, which means your function is increasing. Now, different problems are going to ask different things here. On this one, it just asks, the first derivative test shows that the greatest critical point of f is a local minimum. So be careful how you answer these questions. The greatest critical point is 1 in this case, and clearly the greatest critical point would be a minimum. Now, even if I hadn't drawn this picture, you should know that. Why should you know that? Because we can see right here, from -1 to 1, the function is decreasing. So it's going to decrease down until it gets to 1. Then after 1, it's going to increase. So whether or not I drew this out over here, we should know, okay, it's decreasing before 1, it's increasing after 1, thus there is a minimum at 1. And you'd say, yeah, that's true in this case. Now, up next, we have a problem with a restricted domain in this one, and it doesn't mention that restriction, but you need to be thinking about it. So the problem that they give me is 7x to the third plus 7x to the negative third. Remember that second term represents 7 over x cubed. So you'd say, well, since it represents 7 over x cubed, you know that that denominator cannot be 0. So I just put that in parentheses here. Note your derivative, note that x cannot equal 0. Now, what I started to say is that the derivative cannot have an x value of 0 either, which is certainly true. Now, when I plug or when I try to find my derivative, I can say, well, easy, power rule, 21x to the second, and then be a little careful on the second one. You'd have a minus 21x, and when you subtract 1, it becomes negative 4. I could see a lot of students making a careless mistake and saying negative second there. You're subtracting 1, so it becomes negative fourth. We set that equal to 0. Well, I can always set things equal to 0 more easily if I can factor. So I'm going to factor out the 21, and we always factor out the smaller power of the variable. Clearly, that's x to the negative fourth here. So you'll factor out a 21x to the negative fourth. When you do that, the first term, this x had 6 powers of x more than this term did. So whenever you factor out an x to the negative fourth, this is going to be left with x to the sixth. And then we have minus, well, you factored all that out, so you have minus a 1 for the second term. We set that equal to 0. This first factor, please understand, it literally means 21 divided by x to the fourth. There's no term of x that could ever make 21 divided by x to the fourth equal to 0. So I just say, well, the first factor can't equal 0. The second factor could equal 0 if x to the sixth is equal to 1. That means x can equal, and here's again where students make a careless mistake. They'll just say, hey, the sixth root of 1 is 1. Anytime you take the even root of both sides, the side not containing the variable has to be positive or negative. So you say, well, your critical points are going to be positive or negative 1 in this case. So now I break up the domain of my original problem with these critical points. So I go from negative infinity up to the first critical point, negative 1. Now keep in mind, this function does not exist at 0. So then I go from negative 1 to 0, then from 0 to my next critical point at 1. Then I go from 1 to infinity. I have 4 test regions to look at this time. I choose test points that fit within each of those. I chose negative 5 for the first one, negative 1/2 for the second one. 1/2 fits between 0 and 1, and then 5 certainly fits between 1 and infinity. Again, you could have chose 2 there. You could have chose 1.5. Nothing special about these values other than they are within the region that they're supposed to be. Now, I went ahead and I put my factored first derivative here. My factored first derivative is 21 over x to the fourth times x to the sixth minus 1. And I just needed to know if this product is positive or negative at each of these test points. Now, the first thing I do, and notice the 21 over x to the fourth, it didn't contribute to any critical points. It's also not going to contribute to any sign changes, because no matter what you plug in for x, 21 over x to the fourth power is always a positive factor. So the only factor that's going to contribute to a sign change is the second one. If you plug a negative 5 into the second one, you're going to get a positive. If you plug a negative 1/2 into the second one, you're going to get a negative, because you'd have 1 over 64 minus 1. And then when you plug a 1/2 in, same thing, you're going to get a negative because that 1/2 to the sixth power is tiny. When you plug in a 5, again, you're going to get a positive. So now I'm looking, well, this first region is going to have a positive times a positive. I know that my derivative is going to be positive in that region, which tells me that the function is increasing in that region. In the second region, you have a positive times a negative. The third region, you have a positive times a negative. So I know it's decreasing from -1 to 0, and then it decreases from 0 to 1. And then what do I know about the function after 1? Well, I know that the derivative was positive, so I know that the function increases. So now when I try to determine any maximum minimum values, I know that my function is increasing all the way until I get to -1, and then it decreases. So I know x equals -1 is a maximum. The other thing I know here is that the function continually decreases until I get to the critical point at 1. After that, it increased, which means 1 is a minimum. Now, making sure what they ask in this one, they just ask for the critical points, -1 and 1. And then the first derivative test shows that the greatest critical point of f is a local minimum. So whenever you're thinking of how to answer that, you say the greatest critical point. Well, the greatest critical point is 1. Is 1 a minimum? Yeah, because it's decreasing before 1, it's increasing after. So I can say that's true. Sometimes their questions are a little tricky though, so you got to be careful. Number 10, we have a simple quadratic. Y is equal to -x² plus 8x plus 4. We're trying to find the critical points, and then we're going to determine whether it's increasing or decreasing on each side of that critical point. Now, just because we know how a negative parabola is, its only critical point is going to be a maximum. So you know it's going to be increasing before it and decreasing after it. So you could answer these two questions without any calculus knowledge whatsoever. But let's use the calculus knowledge. So we'll say, all right, here's my quadratic function. I take its derivative, and the derivative is going to be -2x plus 8. I set that equal to 0. And I can say, well, that's going to be true when 8 is equal to 2x or when x is equal to 4. So then I can say, well, all right, my only critical point is x equals 4. I need to find out what's happening on each side. So my first test interval goes -infinity to 4. My second one will go from 4 to infinity. I plug a 0 into my first one. I'll plug a 10 into my second one. When I plug that 0 in, what do I plug it into? I plug it into my first derivative. There was no need to factor it this time. If you evaluate this first derivative at 0, clearly you'll get a +8. If you evaluate it at 10, you would get a -20 plus. It'd be a -12. The only thing I need to know is that it's negative. So we know our function is increasing before it hits 4, and then it decreases everywhere after 4. So clearly there is a maximum at 4, and we can say it's increasing before, decreasing after. And that's all I did here. The critical point was 4, increasing before, decreasing after. For question 11. So in this one, it's asking a little bit more. It still gives me a quadratic, so it should be pretty quick and pretty easy. I have f of x is equal to 3x² minus 7x minus 22. I take the derivative, 6x minus 7, just power rule. Set that derivative equal to 0 to find my critical points, and I would get x, or 6x is equal to 7, so x is equal to 7/6. I break up the domain of the original function with 7/6. So I go from -infinity up to 7/6, and then from 7/6 to infinity. I choose test points within each of these regions, some number between -infinity and 7/6. Anytime 0 is within a region, I always try to choose it. So 0 is in that region, I'll put a 0. Some number between 7/6 and infinity, I chose a 2. Now I'm plugging that into my first derivative. There was no need to factor it this time. When you plug a 0 in, clearly it's a negative. When you plug a 2 in, you'd get a +5. So I know it's decreasing before the critical point. It's increasing after the critical point. We're going to have a minimum at that critical point at x equals 7/6. So now you'll see the first question it asks here is to find the x coordinate of the critical point that corresponds to a local minimum. Like I said, we had a minimum at 7/6. Now, this one then goes in and says, well, what's the critical points of any coordinate that's a local maximum? You just have to be sure to put does not at your D and E for does not exist. There was no critical point that was a maximum in this problem. And then it wants the intervals of increasing, decreasing. You can get that by just looking at your first derivative chart. Clearly, it's decreasing from negative infinity to 7 over 6. It's increasing from 7 over 6 to infinity. And that's all I put there. Last question I'll do in this video, and then we'll do a second video for problems 13 through 22. Number 12 here. I liked this one. 12, you had the first problem that's going to require us to use the product rule. We have y as a function x times x minus 7 to the 7th. So I said, well, derivative of the first is 1 times the second plus the first x times the derivative of the 7 of the second. The 7 came down in front, multiplied that x, then I had the group x minus 7 raised to the 6th power times the derivative of the inside, which is just a 1. So now I have my derivative, but before I can try to set it equal to 0 to find my critical points, I want a factored derivative. So I can say, okay, it's a fact. We can factor that. I can factor out an x minus 7 to the 6th power. That's my greatest common factor. When I do that, I'll be left with an x minus 7 to the first for the first term and a plus 7x for the second term. We need to set this equal to 0. Before I do that, I'm going to simplify that second factor. We have x minus 7 to the 6th times the group. We'll have x plus 7x is 8x minus 7. So now I can say, okay, I have my x minus 7 to the 6th times 8x minus 7 set equal to 0. This is true if the first factor equals 0, and that would give me x is equal to 7, or if the second factor is equal to 0, and that would give me 8x equals 7, so x is equal to 7 over 8. I take these two critical points, I break up the infinite domain from negative infinity to infinity with these critical points, so it goes from negative infinity to the lower critical point, 7 over 8, then from 7 over 8 to 7, and then from 7 to infinity. I choose test points in each of the regions. And like I was saying in the last problem, anytime 0 is in a region, I try to choose it. 0 fits the first one. Some number between 7 over 8 and 7, I chose 5. Some number between 7 and infinity, I chose 10. Now, what are we doing with those test points? We're plugging them into our factored version of our first derivative. Now, I already know that x minus 7 to the 6th, no matter what value of x I plug into that, it's always going to be a positive because a number raised to an even power is a positive. So I can just say, well, no matter what test point I plug in, that first factor is positive. It's the second factor that's going to be changing signs. When I plug a 0 into it, it's negative. When I plug a 5 into it, you would have 40 minus 7 be positive. When I plug a 10 into it, it's even more positive. It'd be 80 minus 7. So then I can see, okay, this curve starts off with a negative derivative up until it gets to 7 over 8, which means that curve is continually decreasing until it gets to 7 over 8. But then it's increasing from 7 over 8 to 7. Now, I wanted to go ahead and draw this out because sometimes students think, well, if it's increasing before 7 and it's increasing after 7, why can't I just say it's increasing from 7 over 8 to infinity? Because it's not. The fact that 7 is a critical point means the slope flattens off there. So this graph is going to look like what I've drawn out over here. And you can see, oh, okay, 7 is not going to be a maximum or a minimum. It slowed down its rate of increase and flattened out before it, but then right after it, it started increasing again. So 7 is not a maximum or a minimum. 7 over 8 is my minimum, but both are critical points. So I go in here and I can say, well, my critical points, 7 over 8 and 7. Determine if the function is increasing or decreasing between the minimum critical point and the maximum critical point. So please make sure you understand what they're asking there, Cmin to Cmax. Well, what's happening between the minimum critical point and the maximum critical point? The function's increasing. So I can say increasing there. And then it says use the first derivative test to determine whether the maximum critical point is a local minimum or maximum or neither. And that's what I was discussing. Since the derivative is positive before it and positive after it, it didn't change sign. Thus, x equals 7 is neither a maximum nor a minimum, even though it is still a critical point. Later on in the next section, we'll be calling 7 an inflection point. It's a point where the graph changed concavity. It would be concave down before and concave up after. But that's for the next section. All right, speaking of next section, the next video will be posted for this very soon. In fact, I'll probably go ahead and do it, but I want to stop here just to make sure my Zoom account doesn't stop me and block off all that I've done so far on this video. So if you have any questions, let me know.